In this first part of the problem, we need to figure out which one of these two electric fields are actually correct electric fields, which ones obey the principle that the curl of E actually equals to 0. That's one way that we can check it. So I went ahead and pre-wrote out what the curl of E is, and then you can find this in the back of the textbook for Griffiths. But the definition of curl of some sort of vector field is equal to all this right here. And like I said, if you have any questions, it's in the cover or the back cover of the electric field or the textbook. So we can go ahead and start chugging along in all these different values here. And again, that's your first line of defense in trying to figure out whether or not electric fields are proper electric fields, is to see if they obey one of Maxwell's equations, which we haven't really gotten to Maxwell's equations, but the curl of E is one of Maxwell's equations, and it's true no matter what, as long as we're not dealing with relativistic stuff. But we're going too far down the line at that point. So the partial derivative of the electric field here in respect to y of specifically just the z component is just going to be 0. And for this portion right here, for the y component in terms of z, it's just going to be 2y. And so that's our x component here. And we'll just keep going on. Right now, the partial of the x component in respect to z is 0. The partial of x in respect to z is going to be, let's see here, 3z. This is the y hat component, and the partial of the y component in respect to x is 0. The partial of y in respect to the x component is just x, and that's going to be pointing in the z hat direction. Whenever we step back and look at all this, it's going to be almost obviously equal to something that's not 0. So we know that this is not a good electric field here. A is not a good electric field. So the question asks which one of these two is the correct electric field. So I guess by deduction we could just go ahead and say that B is the correct one, because we know that the first one is not. But let's go ahead and go through the motions to make sure that we didn't do anything wrong. So let's see here. We got the K. Always make sure to bring out the K. So the partial, let's see here, the partial of the z component in respect to y is going to be 2z. Then we have another 2z here. For the next one, let's see here, partial of z, or the partial of the x component in respect to the z component is going to be 0. Partial of the z component in respect to x is going to be 0. And then partial of our y component in respect to x is going to be 2y, and the same thing for the x component in the partial in respect to y, and that's our z component, and bracket, as you can see, all those equal to 0, and that's good. So this is the electric field that we're going to be working with going forward. So the next part of the problem is involving us to find the potential. So I'll just go ahead and write that here, just to denote us moving to the next section here. Let's see here, denoting to the next section. I'll go ahead and drop this down so we don't have to rewrite everything. So we know that the definition of the potential in respect to R, potential as a function of position, is equal to the negative integral of some sort of reference point, which is the fancy R here, to some sort of point in space as pointed by a vector. And that integral is evaluated along the dot between the electric field and some sort of path here. It's a path integral, right? And our goal is to find the electric field from the origin to some arbitrary point out in space. So let's go ahead and just write out our coordinate axis here. Let's see here, we have our x, excuse me. Let me make sure, there we go. We have our x component, our y component, and our z component pointing out towards us. Let's see here, let's move it over here. So we're going to try to find the path, the line integral in some point out in space where we'll just go ahead and put it in this quadrant right here, right? So this point, we'll just call it this point, where this point is equal to, let's see here, x prime, y prime, z prime. That's the point that we're, the arbitrary point. We could just use x, y, and z, but that's going to get kind of messy whenever we input all these, because these are not prime. We could do it either way, right? As long as you can do the proper bookkeeping. But this is our point. We could have made it in any other quadrant, or down here, but it just makes it easier if we just, in the general point, we use all of the positives essentially. So we're going to do a path integral to this point dotted along the electric field, right? So that means we're going to have to do 3 different segments. We're going to have to do, and again, it doesn't matter what order we do it in. I'm just going to go ahead and do it in terms of X, Y, Z order. So first we'll evaluate it from the origin all the way to the point X prime, and then we'll go up along the XY plane with no Z component, and we'll go all the way to the Y component. So X and Y prime are non-zero values, but Z is still a 0 value. And then finally on the third leg, we'll push all the way out into the Z component and finally get to this dot. And that will be, all these components will be equal to non-zero. So on this first leg, only X is equal to non-zero. And then when we go up, X and Y are non-zero, but Z is 0. And then when we finally push out to here, all these are non-zero. And it's going to make more sense whenever we do the integrals. So let me go ahead and write those out for you right now. So the way we're going to do it is that this right here is going to be expanded into 3 integrals, all being added together. So we'll go ahead and write the first one. So it's from, the first one's from 0 to x. And again, since this will make a little bit more sense here. So dl is actually equal to dx x prime. And this is why things are going to be a little bit different. So dx x prime, dy y prime, dz z prime, right? Because it's a vector. It's got the vector sign on top, right? So that means we're going to have to dot all the components with all of these. And obviously, if it's a x component with the electric field dot with the y component, it's going to be 0. But we'll go ahead and walk through all the steps right here. So let's see here if I can go ahead and paste. Let's see. Let's move our electric field there, our great little picture over a little bit. There we go. Don't need to do much redundancy here. Let's go ahead and just make sure this color is the same. There we go. Okay. So actually, this is dotted with dot dx x prime. And then let's see here. Then we'll add the next one, which is a negative integral. Actually, you know what? We'll just do this. There we go. I'll fill it all in, just trying to get the integrals all out for you guys. So this one's actually, this is the y leg, this is the z leg, and this is being dotted with dy y hat, dz z hat, right? All right, so let's go ahead, and if we look at all these, obviously since this is a dot x hat, right? Anything that's not an x hat here is going to go to 0, so this will be 0. This is 0. These are dotted with a y hat, so non-y hats are going to go to 0, and this is a z hat, and so all the non-z hats are going to go to 0. And we'll go ahead and write this out on our general potential is. So we'll go ahead and pull out a negative k. We'll do the big brackets here to capture all the integrals. So we have the from 0 to x integral of y. And again, I'll add a little something to help explain it. It's from 0 to y of 2xy plus, and this is the y component, And then finally, here's the z leg. 2yz dz, right? And here's the thing. Remember I talked about how we were going to do different legs, different segments of the x, y, and z until we get to the point? And that's exactly what we're going to do here. So the first thing is that for the y component, we're only doing that y component, like I said, where we're going all the way to x is equal to x prime, and then y is equal to 0 and z is equal to 0 because we haven't done those legs yet. For the y leg, we're going to do that x is equal to x prime, y is equal to y prime, but z is still 0 because we haven't done the z leg yet. And then finally, we're evaluating these at all of them have non-zero values, right? And so first, we're going to make sure that we plug these values into the legs first, and then we evaluate the integral. We could have done them in different orders, but it doesn't really matter at that point. You can try it for yourself. It's going to all come out to be the same values. So when we evaluate the integral, this is going to be the integral of 0 because y is equal to 0. So that's just going to be 0, and then plus the integral of this will turn into so this will be x prime y prime, but this will be 0 because z is equal to 0. So the integral of that is equal to, let's see here, 2 x prime, oops, that's not a very good x prime y prime squared over 2, and then plus 0 because integral of 0 is 0 for this portion right here. And then finally, these are all going to be equal to non-zero values, so we'll just evaluate that integral. That's all divided by 2. Of course, just for some bookkeeping here, make sure we get those out of the way. And the brackets. And then finally, what we arrive here is our negative k. X prime y prime squared plus y prime z squared. And that is our potential, in case you forgot exactly what we were trying to do. So that's our potential. I'll go ahead and just drop that down here. That's our potential. And now the final portion of the question is to try to step back and look at this thing, and just to make sure that's right. And the way we make sure that's right is we take the negative gradient of the potential that we had here. And what the negative gradient is, and again, this is, you can reference from either chapter 1 or the back of the textbook, the back cover of the textbook. What it is, it's the negative, and then it's the partial of each component type of the potential, and then pointing in the direction of that component. So this will be partial of y of the potential pointing in the y hat direction, and this is the partial of z of the potential pointing in the z hat direction. And so we'll just go ahead and apply those. We'll look at the v, so the partial of the x, partial of x in respect to all this stuff. And one common factor, of course, is going to be k, so we'll just go ahead and drop k out. But the partial of x of the potential right here, that's just going to be equal to y squared, and that's pointing in the, of course, in the x hat direction. Partial of the y, pointing in the y hat direction. All this stuff. Take a step back. This would be plus. Take a step back. Let's make a better parentheses. Is 2xy. These are all you put primes on here, but you don't have to necessarily do that. They're interchangeable, both x and y, or x prime, y non-prime, whatever. What we're talking about here are just arbitrary points out in space, and the reason why we put the primes on them in the first place was just to make sure that we didn't get them mixed up. It's always proper to do that in whenever you do integration, but for consistency, I'll just go ahead and put the primes on all these. So that's for the z component right there, and brackets. So now we take a step back and we look at what we got. It's actually, we can just go ahead, because this is just the 0 right here. Scoot it a little bit closer, make sure that they're comfortable. Now we take a step back and we look at our original electric field. When we go all the way back here, look at our original electric field. It's the exact same thing, y squared, and all the rest of the components. So y squared and all the rest of the components are going to be the same. Recommend them, of course, that you do check them yourself, but it does look like, in fact, we did it correctly, that the potential that we got does end up being like the electric field.